In this video, I'm going to talk about designing codes for exact repair. I'm Sai, and this is a part of mini project for my course CSE 545. Video requires a background knowledge of error correcting codes, which I'll briefly survey here, and also some basic linear algebra. So, what is a code? A code is typically characterized by four parameters. One is the alphabet size on which the code is constructed, the code word length, the message length, and minimum distance. So we now have sufficient background to define the problem of exact repair. So here, for example, let's say you have four nodes, four symbols from the code, C1, C2, C3, C4, and now suddenly one of them fails, okay? Say, let's say C1 fails. And now the question that we are interested in is, what is the least number of symbols that we need to download from the remaining nodes in order to repair C1? And that's what we would be discussing throughout this video. Why is this question interesting? The point is these single node failures are sort of the most common failures that occur in real-time systems, and there have been works that simply address this one problem. So basically, they try to design codes that can handle the single node failure efficiently. And so this is some discussion. Typically, erasure coding is used when you're working with warm or cold data, that is data that's not accessed that frequently. And then, so Facebook has done some work here where they have tried to address this using using a set of codes called the piggybacked Reed-Solomon code. And Microsoft again they have taken a different route, and then they have this notion called the locally repairable code, and they have tried to attack this problem from that end. Now, the natural question is, once you have that exact repair problem, why don't you go with MDS codes? Because MDS codes, we know that they give us the best distance. Distance is exactly n minus k plus 1, so you can correct up to n minus k erasures. And another important point, so mostly we will talk about, when I said even like when C1 fails, a single node fails, we will talk about erasures, but not worst case errors, because we know that we know where the failure has happened, okay? And we know a good class of well-used MDS codes, Reed-Solomon codes, which I just mentioned earlier. Now the thing is, but there is a huge disadvantage of MDS codes in the sense that even if you have to repair one symbol failure, you still need to download whatever is there in any of the dimension number of symbols. And so let's say each node, when each symbol is of size L or whatever, then you need to download KL symbols to even for like one symbol failure. So it's only natural that they are not specialized for this exact repair. So can we do better as an instance? So can we have codes that actually are specialized to handle this type of? So yes, of course, else this video wouldn't exist. And such codes are called MSR codes, the minimum storage regenerating codes. And what happens with these codes? So these codes are typically characterized by 5 parameters. And one is obviously the length of the code word, and you have the number of parity symbols instead of dimensions. Some folks here care about the number of parity symbols, which is essentially n minus k, where k is the message length. And then you have the subpacketization, you have the number of helper nodes, and then you also have alphabet size. Okay. Now, what about the distance? Okay, so here you're going to talk about distance, which is at the node across nodes, and each node, the subpacketization is a new term, right? In the sense that here, what you're saying is each node has a size. In some sense, you're going to treat each symbol as a vector. Okay. So the point is, the distance can be defined in multiple ways, but in the most commonly accepted way, it is defined at the vector level, in the sense that you compare vectors and then you see in how many symbols they match and mismatch. And then based on that, you define the notion of distance. But for all purposes of our whatever we're going to do, it does. Now, so the question is, are there constructions of MSR codes? It turns out that yes, and there is like very recent work that settled this problem, at least for high rate codes, which are what are frequently used. Low rate, we don't care, we might as well replicate. So I'm going to describe here a code in a really elegant code, one of my favorite constructions by A. N. Barg, which came in 2017 in a paper. And there, what we're going to have is, and I'm going to set some parameters just for niceness of all purposes of this video, and things are just going to nicely generalize. It's a very cute construction. So what parameters are we going to set? So we're going to say n is 4, r is 2, okay, and l is r raised to n, so it is 2 raised to n, which is 16 in this case. And this code is constructed, and the number of helper nodes is 3. That is, I'm going to contact all the remaining nodes, and that limitation can be overcome, but we are not going to go there. We are going to assume that you can contact all the available nodes. Now the point is, this is constructed over again a linear field size, something in n, and n is constant here, so really it doesn't matter. And I also have scalars of the form gij, where for this I is there for each node, basically from 1 to 4, and j is from 0 to 1. You will see how I'm going to use them. And these exist. It's not too hard to see that these exist these can exist in a finite field of almost like linear size. Now, the way I'm going to define this code is using a parity check matrix. So what I'm going to do is I'm going to define a R cross n, which is essentially RL cross NL, but I'm going to define them as block matrices. So you have H11 to H14 in one row, H21 to H24 in another row. And so if you see, each block matrix that I have is a diagonal matrix with entries of the form G, J, comma A of J raised to I minus 1. Okay. So when for the first row, essentially you just have 1 because I is 1, right? So yeah. But what does AJ? This AJ is the interesting quantity here. So what it is basically you do the binary representation of A. So you run, it's a diagonal matrix, and A is the only parameter that I'm moving, right? So J is fixed. So A goes from 1 to 16. And so you can assume that it goes from 0 to 15. And this A of J is the J bit from the left to the binary representation of it. Okay. And that's all that I'm going to write. Now, how does this code give a solution for exact repair? So what was the question again? The question was that what is the least number of symbols that need to be downloaded from each remaining node to repair C1? Okay. It turns out that this quantity is actually bounded by L by R. This is there in a seminal paper of Demakis et al. In 2007. And that is exactly 2 raised to n minus 1 in this case. So what you're doing is from each node, you're downloading only L by R symbols, and in total, you're downloading n minus 1 times L by R, which is n minus 1 times 2 raised to n minus 1. And that can be much better than k raised to 2n in the hierarchy. So now the point is, how can you achieve this? And this is where this A of J's binary representation comes into the picture. So in this slide, I'll actually sketch how this exact repair bound is achieved. So what I've done here is I'm just going to show the repair of 2 symbols in C1, C10 and C11, and I've written the parity check coefficients corresponding to these 2 symbols. There are 4 of them since R is 2. Now the question is, how am I going to do the repair? So what I'm going to do is I'm going to sum the alternative rows, and then I've written down what the sum looks like. So from what you can see, you see that while you have rank 2 type equations for C10 and C11, all of the other ones you need only one scalar to sort of compute the thing. So for each 2 bits, you need like 1 symbol from each remaining node. And so overall for 2 raised to n, you need 2 raised to n minus 1. And that completes the proof.